Okay. Oh, is it done? Okay. Okay. So welcome to the first session for today. So we have Pulkit here with us. So Pulkit is an assistant prof from the Department of Electrical Engineering and Computer Science at MIT. He earned his PhD from UC Berkeley and co-founded Safely U Inc. His research interests span robotics, deep learning, computer vision, and reinforcement learning. Pulkit completed his bachelor's from IIT Kanpur and was awarded the Director's Gold Medal. His work has appeared multiple times in MIT Tech Review, Quanta, New Scientist, New Post, etc. He is a recipient of Sony Faculty Research Award, Signatures Fellow Award, Fulbright Science and Technology Award, Goldman Sachs Global Leadership Award, OPJEMS and Sridhar Memorial Prize, among others. Pulkit holds a Sangeet Prabhakar and occasionally performs music in concerts. Uh, so, with that, we'll hand over the stage to Pulkit so you can start.
Good morning, everyone. So I guess I can't see you, but hopefully you can see me. And I'm hoping I'm also audible. So I'll get started. And thanks for inviting me. It's a pleasure to be here. It's kind of strange that I can't see anyone, but I'll assume that everyone is there. So let me start by giving you this example, right? So what you see in your front is a screen, and this is actually a video game. So if you'll see, there's an agent which seems to be going up and down, right? It kind of goes on the right, it falls down, and it appears again. So what's happening over here? What is the goal of this agent? Just by looking at this video, it's very hard to say what is this agent trying to do. But what if I told you this is simply a re-rendering of the following, right? So now you clearly know that there's an agent which probably wants to kill the pink sprite, jump over platforms, get the key, and then go to the door, right? So as humans, we can make a lot of interpretations about this game and know what the agent has to do because we are bringing in a lot of prior knowledge that we have, that keys open doors, we can climb over ladders, we can climb on platforms, and so on and so forth. Right? So we can go on and compare how humans perform on these two versions of the game, right? And as you see, humans are much faster at solving the original game as compared to the modified game, which has a lot of different textures to re-render the game, right? So on the right, what you see are the bar plots showing that humans take a lot of time when they are given these new kind of games instead of the original version of the games. Okay? But what about reinforcement learning agents? How do computers do when they are given two different versions of the game? So as we saw earlier, for humans, the performance is different. Humans do much better on the original version of the game. Whereas if we look at reinforcement learning agents, they do about the same. Right? So what this tells us is that while humans are able to bring in a lot of prior knowledge about the world and use them to solve new tasks efficiently, this prior knowledge, what we call as common sense, whereas reinforcement learning agents have no such knowledge about the world. And this is probably one of the reasons why these agents are so inefficient, and you hear about that reinforcement learning agents, while successful, require millions and millions of examples to succeed on a particular task. Okay? So the whole question is, how do we end up building agents which can solve, new tasks efficiently? By efficiently, I mean either they can solve more complex tasks or solve them in much lesser time as compared to the tasks they have done in the past. Okay? So one possibility is that we equip our artificial agents with the same kind of prior knowledge that humans have. Okay? So one way of doing this is to hand design, this kind of common sense of prior knowledge, and this used to be a popular approach, decades ago. The other approach is where we can have systems which can discover this knowledge about the world from their experience. And in this talk, I'm going to focus on this particular aspect. And if we look at learning from experience, broadly, there are two categories in which we can divide it. One is a model-free approach, which simply means that I'll have my artificial agent, which I'll train on a large number of tasks, and then hope that I can solve new tasks much faster. So this is similar to what people are familiar with ImageNet, that once you train a deep network on ImageNet, you end up learning visual features which help you solve new vision tasks much faster than training from scratch. Although in context of building sensory motor agents or agents that act, there are multiple problems. For example, transfer in reinforcement learning is very limited, and there's some problems associated with continual learning and catastrophic forgetting, something which I'll touch upon later in the talk. Right? And the other approach is, instead of just solving a large number of tasks, we can try to explicitly understand how the environment works so that we can use this knowledge to solve new tasks, right? So what do I mean by understanding of the environment? For example, knowledge of physics is one sort of understanding, and physics is a model about how the world works. Right? So in our lab, the kind of approach we follow is where we have some robotic systems which explore the world to collect their own data. For example, on the top, you're seeing this robot continuously trying to push these objects to understand how it might push objects. Right? And on the bottom of your screen, you again see robots playing with a rope. So it just picks up the rope and keeps it and repeats this process over and over again for a long period of time. And similarly, on your bottom left, you see a robot again trying to explore its office environments. Right? So these robots are trying to learn about the environment by exploring on their own. And what are they doing during this exploration is, they see the current observation, which is, let's say, image XT. They conduct an experiment, which is they take an action, AT, and that leads them to the next image, right? So now we have this data, which is my current observation, the action I take, and the next observation. And then, using this data, these agents are building models, right? So the question is, what kind of model should we build, right? So one useful model is a model which can predict what is going to happen next, because then we can use such a model to plan our actions, right? So let us assume I have inputs XT and AT, and I want to predict what is going to happen next. Right? So one popular approach has been to build these models in pixel space, right? So what do I mean by pixel space is you predict the value of every pixel in the future. So you want to ascertain how the world would be in the future, pixel by pixel, right? And there has been a lot of work in this area. However, it turns out this is a very, very hard problem because it's very hard to predict how every pixel is going to be. But more than that, the problem is hard, but is this also the right problem to be solving? To see this, consider a glass bottle. And what I say is I'm going to drop this glass bottle. Right? Now, do you really want to predict where all these pieces of glass goes or where every drop of water goes? Probably not. Right? Probably what you're interested in is the fact that the bottle breaks. Right? And that is sufficient for you to not step over the water and go about your business. Right? So what you want to do is we want to figure out these kind of abstractions which are useful for acting without worrying ourselves with the minute details which are hard and also not required. Right? So instead of predicting pixels, right, we want to do something else. Right? We don't want to predict pure pixels. So what can we do? Right? So there has been a large body of work which has looked at that instead of having images XT and predicting image XT plus 1, we try to learn some kind of a feature space over here Z, which has been transformed from the original image, goes to a neural network, and it gives you some feature space Z. Right? And the question is, how do we learn a good feature space? So one thing that we have explored in our lab is that instead of trying to predict the next image, we can actually predict the action. Right? So given the image XT and XT plus 1, we'll pose the problem as predict the action which takes you from image XT to image XT plus 1, and we call this the inverse model. And it turns out that by solving this problem, we can learn useful features. So we can overcome this limitation of predicting in the pixel space by jointly training an inverse model and a forward model. Okay? So now this is what these robots are doing as they're collecting data. they're training these forward and inverse models. So now let's look at how these robots perform when they are subjected to new tasks that are given to them. Right? So for example, over here, you see the current state of the world shown on the left and the goal state shown on the right. So the robot is provided with just these two images, and it is tasked to perform a sequence of actions so it can transform the world from the current state to the goal state. Right? So let's see what the agent ends up doing. So over here, what you're seeing is the performance of the robot on new objects it has never seen before. Right? So over here, for example, it's able to put the red pyramid in shape. Over here, it's trying to push a car. Right? Okay, I mean, this is pushing objects on a planar table. Not very surprising that a system can do this. Right? But let's consider another task. Right? So you saw that a robot was playing around with the ropes. And now what we tasked the robot was with this target image shown on the top right, which is showing a knot. So the question is, given the current state of how the world is, and given just the target image, can the robot actually go and perform this task? Right? So let's see what a system ends up doing. And what you see over here is that the robot is able to go and tie the knot. I mean, just as a disclaimer, the performance is not 100%. It's about 65% on this task. But it's still much, much, much better than random chance. Right? So what this is showing is that the robot is able to extrapolate and go beyond what it was trained for, because the chances of getting a knot by random exploration is almost nil. Right? Similarly, we can see in the case of navigation. So remember, again, a robot which was exploring its office environments. Now we put this robot into a completely new office. It has no map, it has no 3D sensors, all it has these images, right? So it sees the current image is what its camera is seeing right now, and we give it a goal image and ask the robot to go there, right? So now in this scenario, there is no overlap between the current and the goal image. So what would one do? As a normal human, you would probably look around and try to find where the goal image is and then go towards it. Let's see what a system ends up doing. So you see this behavior where the system goes around and then it tries to go towards the goal image. So in some ways, there exist systems such as SLAM, which can solve this problem. But over here, this phenomena is emergent. We did not have to hard code the fact that the robot has to turn around and then go to the goal image. It is something that emerged out of our system. Right? So these are just showing some examples of how a robot can go on and collect data and use this data to build useful models to solve new tasks it might not have encountered before. Right? So in a nutshell, what our system is doing is it is running some experiments to collect data, and then it condenses this data into a model of how things work. And this model in turn tells the robot what experiments to run. Now, in general, there is too much to learn in the world. So sometimes you bias what you learn by observing other agents or getting some expert supervision. So I'm not going to cover this as part of this talk, but I'm happy to talk about it. And then with any machine learning system, another question is, what is the initial state that you start off from? Okay? So these are broadly the 4 questions that we try to address in the research theme that we call computational sensory motor learning. Okay? So think of this as a mechanism by which the agent is learning about the world. Right? So now that I have gained this knowledge about the world, I want to go on and solve new tasks. So now let's look at some issues which come up when we try to use the systems for this. So one general thing which happens is, as we learn about new things, we tend to forget older things. Okay? To illustrate this fact, for example, I can first train my computer vision system to classify images into 10 classes as part of this CFAR dataset. Okay? And then I can have a second task where I have some other images coming from some other 10 classes that I now need to classify. Right? So now let's see what happens when we measure performance. Right? So what you see is that initially the performance of the system is high when it is trained on task 1. So on the x-axis, what you're seeing is the number of training steps, and the y-axis is accuracy at that particular task. So at 20,000, we change the task. We go from task 1 to task 2. And what we are measuring is the accuracy on task 1. Right? So what you see is the more we train on task 2, the more we tend to forget task 1. Now, this is a bad thing because if we really want to gain this common sense knowledge and knowledge about the world, we don't really want to forget, what happened some time back. And so we want to remember this. So what can we do? Right? So one simple approach could be that I can have separate neural networks per task. But this is not an ideal solution. The reason is that one problem is scalability, that you need to have one network per task, but maybe that is all right. But the more critical problem is that there's no way we can transfer knowledge between tasks because each network is separate and they don't communicate with each other. Right? So in an attempt to solve this problem, we came up with one potential solution. This was work led by Brian Chung and presented in NeurIPS last year. And the idea is, pretty simple. The idea is that instead of having these weights, instead of having these separate neural networks, we came up with a formulation in which you can store weights in superposition in a single network. Right? So the main intuition behind this is similar to Fourier transform, where even if I have information about multiple frequencies, I can superimpose them together and they don't interfere with each other. So in a similar way, we can develop a scheme in which we can also store weights in superposition and they don't end up interfering with each other. Again, the details of these works can be found in the paper. So now let's see, if this actually works, and it turns out it does, right? So if you look at the blue line, which is the line of the superposition model, so that does not or that the amount of forgetting happening in the superposition model is much lesser as compared to the baseline that we have. So this is, one of our attempts to try to prevent the agent from forgetting what it learned previously. Right? So now let's look at another task and see, an agent trying to, learn something and then trying to go to another task. Right? So what I have over here is a very simple 2D maze. So what you see in the blue is the agent, and the green is the cheese, and the agent is trying to go to the cheese. Right? And what we want is, after training on this task, we want to transfer a new task, which is heist. Over here, you have the agent, and the agent needs to pick up the key, then open the lock, and then finally go and find the diamond. Right? So you want to transfer from maze to heist. Right? So there are visual differences between these tasks. There's a change in the reward structure because in the new task, in the heist task, you need to actually take the key and open the door before you can get to the goal. But what remains same is that the dynamics between the maze and the heist is the same. What I mean by the dynamics is you still have the same actions, left, right, up and down, that you need to move around in the game. Right? So now let's see, how do we approach this problem today? Right? So I have my current image, ST, which is the image of the maze. And I might learn a policy which tells me how to act, right? And this policy could be represented by a neural network. And so I can train this system on, I can train this policy on many, many mazes, and then take this neural network and then try to play heist, right? So now let's go back to the challenges which are there from transferring to maze to heist, right? So first is the problem of visual differences, right? So maybe, if we train with a lot of different mazes, which is called as domain randomization, maybe the problem of visual differences would go away. Right? But what about change in the reward structure? Right? Would the policy trained to solve a different task just generalize to a new task? It's unlikely. But there's something which is common, which is the dynamics of the world does not change. Right? So this is something which is common about our world also, right? No matter if I'm in the kitchen or if I'm driving the car or if I'm, trying to assemble my office furniture, the dynamics of the world is not changing, just the tasks are changing. Right? So it turns out that by exploiting the fact that the dynamics don't change, we can come up with a better solution for transfer. Right? So instead of training a policy which predicts just the current action, what we'll do is we'll predict a sequence of actions. So instead of predicting just AT, we'll predict, say 5 or 10 actions in the future. Right? And what we're going to call this is the extended action trial. So what this is actually encoding is the space of useful action sequences. That is, given in the current state, what are some good sequence of actions I could be doing? Right? So now there has been a lot of work in people attempting to learn good action sequences. But over here, what we're going to show is that if we pose the model in the right way, we can explore better because we have a space of useful actions. And because we can explore better, we can adapt to new rewards quickly. Right? So how would our setup look like? First we use model-free RL algorithms to solve multiple levels. Right? And what this does is it produces us high reward trajectories, which I've just notified from S1 to Sn. Right? Now we're going to rewrite these trajectories so that I have my current state St, and I have a bunch of, say, k actions after each state. So I can segment my trajectories to get my current state and k actions after that. And what I'm going to do is to simply cluster these actions. Right? And in neural network land, we can achieve this clustering by building an autoencoder. So what you see on your left is the state and the sequence of actions, which gets encoded into a latent vector z. And then from z, we are decoding the actions that we encoded. Right? And the other thing that we would also need is to learn when to use which action primitive, right? So we want to figure out that in the current state St, what action primitive to use, right? And with this, we can formulate the problem as trying to cluster the action sequences as well as learning when to use which particular action sequence, right? So in some ways, the latent variable z is capturing the action prior, which is a bunch of useful trajectories, whereas the prior, or whereas this mapping from St to Zt is capturing the visual prior, which is when to use which action primitive. And this was work led by Anurag. So let's see how well it does. So we again train on some training environments, and then we would go to a new environment and test transfer over there. Okay. So now let's first look at, I'm again reminding of the setup. We are trying to go from maze to heist. And then what I'm showing you is performance of training from scratch on heist itself. So the x-axis is the number of time steps, and the y-axis is the reward, right? And then what I'm showing you in blue is the pre-trained policy. So the performance of the pre-trained policy is very similar to the policy from scratch, which means that if I just have my vanilla neural network, there is almost no transfer between these levels. And what we are showing over here is LMP, which is another way of pre-training using sequences of actions, which does not work that well. And EAP is the method that we propose. And over here, you see that if we are able to correctly identify the action sequences, we can transfer really well. Right? So we can investigate transfer in some different settings. Right? For example, we can have the differences only in the visual space, but preserve the rewards and dynamics. So one way of doing this is that we can have the maze task, but we can split up the maze task that we train on 100 mazes and then test on, say, other 100 mazes, right? So if you see over here, again, the performance of our method is better, but it's not as, the gap is not as much because the reward structure is the same, right? Similarly, we can go onto other games, and you would see the same trend is follows. Now we can also go and test a very different setup where everything is different. For example, we have this game of Ninja where the agent needs to shoot and jump over platforms, right? Whereas on the other one, the agent just is jumping on the platform. It doesn't need to shoot. The dynamics are different. The visual structure is different. And even, the reward structure is different. So in this case, pretty much, our method ends up performing as good as Scratch because there's very little to actually transfer. Right? And the same, idea we can use in simulated robotic task, where we can, first pre-train on, pick and place, and then transfer to a bunch of other tasks. Right? And again, the same thing happens. So if you compare with PPO, which is the baseline, which gets around 15% accuracy, we can get, around 70% accuracy with the formulation that I just told you about. So in summary, right? So if we have visual differences, right? So this method of learning action prior improves your transfer. If we have differences both in the reward structure and vision, it helps even more But when there's nothing to transfer, it does not really help you, that much. Now, it's not necessary that we always, learn these skills. Sometimes we can also define these skills and try to use them for some useful tasks. So for example, over here, we'll try to have this robotic system which is trying to get from the start position to the goal position. Now, it's a bimanual robotic system, so it cannot do this operation in one go. And the reason is, first, its hand will not extend from one side of the table to the other side of the table. And second, this block needs to be oriented in 3D, which it cannot do with just one, kind of an action. It has to actually lift the block, the cube, and then rotate it, right? So I'll come to it. And so what we are given is some set of primitive skills, like similar to what we were discussing before, and then we want to string them together into a sequence to perform this task, right? So in particular, we'll have two skills, which is pulling and grasping, right? And the question is, what sequence of intermediate sub-goals and how to actually go about achieving them. So over here, what you see is the system, proposing a sub-goal. First it moves the block to a position where it can actually rotate it using both of its hands. And then after it, grasps and rotates the block, it can then go and, push the block to the desired location using its other hand. So again, so this is work mostly led by Anthony in a lab. And the goal of this work is to move towards long-term planning and directly work with point cloud data instead of assuming we have access to pose of 3D geometry of the object, so that we can easily generalize to a wide variety of object geometries. So for example, you see cuboids of different sizes. And now what you see is the same system trying to manipulate a cylinder. And now it tries to pick up a drill bit and then keep the drill bit. And next you will see trying to rotate a bottle. So what these examples are showing is that the same system, which has been trained only a few objects, can very easily go and manipulate new objects. And most recently, we're trying to train this to keep books on bookshelves. So in a similar spirit, we have some ongoing work where we are trying to learn how to manipulate things from touch sensors. So if you see over here, we have this robotic hand which is covered in touch skin. So all the wires that you see and the covering of the hand are actually all tactile sensors. And we're trying to see if we can make use of tactile sensors to learn useful skills. And the last bit I'm going to talk about is got to do with looking at the training time more closely and seeing if there's something we can do to improve transfer. Right? So if we look at the training pipeline, typically we collect data and then we learn a policy. Right? So typically, in the data collection phase, an agent undergoes an episode. So episode is a bunch of steps the agent takes until either it succeeds or it dies or there is a maximum time limit, right? And let us assume that, overall, the agent has, some number of steps to execute and which we are going to call a trial, right? So the goal of the agent is to maximize its rewards across the trial. And if it achieves a reward early in one episode, the episode will get reset so that the agent has one more chance to maximize its reward. Right? So now what happens is, I've trained a policy by and the training time, and then I go to the test time, right? Now what happens at the test time the agent fails? Well, I repeat the same policy again, but the policy is the same. So nothing is going to happen, right? So what can we do in this scenario? Right? So one solution which some of the previous works come up with was, instead of having a policy which only depends on the current observation, let us have a policy which also depends on previous episodes. So these were some meta-learning based approaches, such as RL² and Snail, which appeared in the past few years. So this kind of works, but there are some problems associated with it, right? And the problem is, suppose I have an agent and it makes a mistake, right? And then, I optimize my policy and I learn to correct this mistake. Now the agent might make some more other mistake, right? Then again, I optimize my policy and I can correct for this new mistake. But then the agent can go back and make the same mistake A, which it made initially. And this becomes a problem. Because the agent is not has a limited window of the past that it is looking over. Right? So instead of looking only on a few episodes in the past, what we would like to remember is a bunch of old failures. Right? And this is what architecture the lead author on this paper Tao came up with was if the agent is failing, it should remember its failures and use these failures so it can succeed at new tasks successfully. So I won't have time to explain all the details, but what I will tell you is that our system, which I'm showing on the red, ends up doing much better than the previous baselines. And I'm going to skip some of these results and go back to this video game example. Right. So over here, what you see is this climber game. From the first episode, the agent goes and it fails, but then it uses this failure to then go and learn not to hit the fish and then succeed. Right. And if you look at the performance, our agent actually does better than what people had proposed previously. And this kind of is consistent across a bunch of games. Right? So in essence, what I talked about was how we can gain this knowledge and then go out and perform new tasks. In particular, we discussed don't forget the past, use the structure in the action space, and then we can use action primitives for flexible planning. And these were some attempts towards gaining and transferring knowledge. And with this, I'll stop.
Okay, great, excellent. Thank you very much, Pulkit. It was a great talk. But unfortunately, because this is online, the audience must be clapping, and we are not able to hear. Of course, every person in the audience is clapping, and you will not be able to hear it. But let's take questions one by one. So we have one question here from Vaibhav. So a task can be performed by many different possible subtasks in many possible sequences. How do you select the best possible sequence of tasks?
So I think this has got to do with the question of planning. So in different works right now, there are different approaches that we have followed. So the first approach is to come up with a good initial guess, and that is what we end up getting through our inverse model. And then we sample around that. And by doing that sampling, we're able to prune the space of solutions. So for example, if you look at the bimanual manipulation task, right, over there, we are trying to search for what is a feasible plan by trying it in simulation because we have a model which can predict what is going to happen in the future. Right? And then we roll out many things in imagination and evaluate that with a reward function and then choose the best one.
Okay, excellent. So we have one more question by Kishan. In the transfer learning part, is there a performance guarantee when the distribution shift is significant?
So there is unfortunately no guarantee right now when the distribution shift is significant. Or even if you look at the adversarial training work, it will show you that even when the distribution shift is very small, there are almost no guarantees. So I think this whole area of robust machine learning, where we are trying to make our systems robust to distribution shifts and have some guarantees, is a very active area of research.
Okay, nice. So we have one last question from Ganesh, senior architect from Wipro. So his question is, can a full search of best evolution solution be possible?
So I'm not sure of what you exactly mean by this, but if the question is, can we always find the global optima? The answer is no. If you meant something else, that can we evolve agents in the same way as life evolved on the planet, then I guess the answer to that is probably also no.
Okay, yeah, I think the second answer was what he was looking for. Okay, so in the interest of time, we will close this session. So thanks a lot again for Pulkit for giving a talk here. Again, like I said, I'm sure everybody in the audience is clapping, and unfortunately, you're not able to hear it. So with that, we will end the session. So thank you, Pulkit.
Yep. Thanks everyone for coming, and thanks for inviting me.
Okay.